Hello, and welcome to Intro to HPC from the Yale Center for Research Computing. My name is Sam Friedman. I'm a member of the research support team at the YCRC. And the purpose of this workshop is to provide an introduction to anyone who is going to be working on the Yale research computing clusters, who is new to HPC, who has never interacted or used a Linux server before. And we're going to be going through an overview of what HPC is, how you access research computing at Yale, and some of the very basics of the things you'll need to know and the things you'll need to use to be able to execute your research on our HPC systems. So here at the bottom of the slide, you can see that we have a link to some examples that are on a GitHub repository. This is a workshop that you'll be doing examples alongside, so feel free to pause the video and work on these as they come up in the slides. And there's a link to these slides as well under this tiny URL. So today the outline for what we're going to be talking about begins with some of the basic HPC information. What is a cluster and how does it work? We're going to show you how to log into the clusters, providing you've already made your accounts. We go through some of the basic useful Linux commands for interacting with data, moving things around, creating and deleting files on the clusters, how you transfer data from outside sources to within the Yale systems, as well as in between different nodes or sources within the Yale systems. We'll show you how to launch interactive jobs where you can type commands and see results, as well as batch jobs where you write scripts that define what the operations you want are and then run them on the cluster and wait for them to finish. Finally, we'll have a Q&A about what we showed today, some of, in our case, the most frequently asked questions, as well as finish with some extra examples for those that want to go a little further in their learning. So, as I mentioned, this is an interactive workshop. Please feel free to follow along on your own. Whenever we have an example on the screen, you can just pause and see if you can figure it out. We go through all the solutions immediately afterwards. Okay, so what is the Yale Center for Research Computing? This is an independent center under the Provost Office, and it was created and founded to support the research computing needs of all researchers at Yale. So the focus is on high performance computing and storage, meaning that we manage all of the hardware and support all of the users on that hardware. We have about 30 staff, which includes application specialists, systems engineers, sysadmins. We are available to consult with and educate users. In fact, my team, the research support team, spends most of our time responding to requests from users, helping them figure out how to get their research running on HPC computers. And you can find our website here at research.computing.yale.edu, and our documentation site is just below. I recommend you bookmark both of those pages. They're very useful. Referencing the documentation site is something that will happen again and again. So, make sure that you know how to find it and how to get there. So, at the very beginning, what is a cluster? So when someone mentions a supercomputer, this is really what they're talking about. It's not so much one gigantic computer that is, larger in every dimension than your typical workstation you have under your desk. It's actually a system of hundreds to thousands of interconnected rack-mounted computers. So where you may be working on a single workstation, we have hundreds, if not thousands of them that are all connected together and all designed to be able to spread the computing across them to reach speeds and efficiencies not possible on a single computer. So why should you use one of these clusters? Well, the obvious answers are if your personal machine is just too slow, doesn't have enough storage, doesn't have enough memory for what it is you're trying to accomplish. We also have a lot of GPU resources. Today, more and more machine learning and AI applications require the specialized processing of a GPU. And some of the clusters have dozens, and some of the newer clusters are going to have even more GPUs. So those are all also available to you. You can request them just as you request the rest of the computing hardware. So if you do have a large number of jobs to run, maybe in your personal computer, you'd be looking at, waiting days while dozens of jobs run back to back and, processing over dozens of different samples. In the cluster environment, you can parallelize these jobs so that once you define how to run for one sample, you can simply send all of the samples off at once, and the cluster will take care of dispatching them to the different parts of itself to run to completion. So we also have a number of different databases, software programs, resources that are already stored and ready to use on the clusters. So anytime someone requests a new piece of software or we find something that may be useful to our researchers, we try to make it available on the clusters so that you don't have to worry about dealing with your own software installations. All of these, pieces of software are already available, and it's just a few commands to make them available for your session. So finally, we have a large support team of which I'm a member. YCRC's research support, spends all of our days improving the clusters, helping people use the clusters, and making videos and workshops like these to allow people to learn a bit more of how to use the clusters and sort of what the capabilities of them are. So the number of clusters at Yale is shrinking actually as we make this video. We are currently we have four clusters available, and we're actually planning two more. One is Boucher, which is our new general purpose cluster, and the other is called Hopper, which was recently announced and is going to be sort of a similar modern cluster to Boucher, but specifically for high risk data such as PHI and HIPAA. So eventually, the current clusters for life sciences, like McCleary and the general purpose Grace cluster, will be subsumed by the new clusters. But for at least for the next year or two, that's not going to be the case. So if you're currently a member of one of the clusters, you don't have to worry about moving any of your data. We're going to be reaching out as that's necessary. But for now, the largest cluster we have is Grace at about 29,000 CPUs, and it's for most of our general purpose and MPI workloads. McCleary has about 13,000 CPUs, and it's primarily focused for the medical and life sciences wings, as well as the YCGA. That's the center that does most of our genomic analysis, genome sequencing, and so on. There's a smaller Milgram cluster that's currently before the launch of Hopper, used for the high-risk data like HIPAA, and the Misha cluster, which is specifically for the use of the Wusai Institute. So, to begin, to access the clusters, they're only accessible from the Yale campus network. So that means you'll need to be on the Yale Secure Wi-Fi. You'll have to be either plugged into the Ethernet if you're on campus, or if you're off campus, the Yale VPN. If you are accessing one of the secure clusters like Milgram or Hopper when it launches, you will need to be on the Yale VPN, even if you're already on the Wi-Fi or plugged into Ethernet. So there are three general methods to log into the clusters. The first is command line, SSH. That's the tool that's typically used to connect to another computer through the terminal. And this is easiest because it is built in through Linux or macOS. If you're on Windows, we recommend a graphical SSH tool. The one that we prefer is called MOBA Xterm, and that is downloadable and installable on Windows. We have links in our documentation as well as through the Yale software library. And then we also have a tool called Open OnDemand, or OOD, and this is a sort of web-based interface. So it's a website that you go to and log in, and then it gives you options to launch apps, launch terminals, and interact with files on the clusters directly through your web browser. So the first two methods rather require SSH and an SSH key, which you should have set up when you created your account. And if not, there are instructions here at our documentation to show you how to create SSH key pair and upload it to the cluster so that you can log in via SSH. How does a cluster work? Well, as I mentioned before, it is not a single computer, but a large network of interconnected computers. And different nodes, that is, the individual computers in the cluster, have different jobs. And so the first node that you ever come into contact with when logging into the cluster is suitably named the login node. And this is just the nodes that are really only for managing the logins. It's the first thing that people connect to, and these are the nodes that people launch jobs from or connect to other nodes from to do the real work on the cluster. There's a shared file system on the cluster, meaning that all the storage that you access is in a large pool of disk drives and solid state drives that provide all of the storage underlying the cluster. And this file system is accessible from all of the nodes in the cluster, and it's connected via some very fast networking, so that in any of the nodes on the cluster, you can access all of the data. The computation, meaning the actual jobs, the real work that you're trying to do on the cluster, happens not on the login node, but on the compute nodes. And as you can see in the diagram, the compute nodes are, far more numerous than the login nodes. In most of our clusters, we have one or two login nodes just to manage people logging in, and dozens of compute nodes that are actually running all of the jobs and all of the computation. So the typical workflow is you'll log in to the login node and then, prepare the scripts or the data that you need for your job before launching that job with that data to one of the compute nodes. So to begin, let's start just our first exercise here. We have the link to the Open On-Demand or OOD interface here at our docs. And I'm just going to walk through, and if you could, just open the web page alongside and learn how to navigate some of our documentation. And this page that we've linked specifically is for the Open On-Demand portal. So you can see that there are links for each of the clusters here that have OOD installed to the OOD site. And when you click these links, you'll find the main dashboard of the OOD app. It looks like this. So this is specifically for the McCleary cluster. You can see that along the top there are some menu options, and the graphics at the bottom show some of the most popular apps that people use on OOD. These are things like Jupyter notebooks for working in Python and R. We have MATLAB interfaces. There's a remote desktop if you just need a graphical desktop on the cluster to run graphical apps. That's perfectly available, as well as RStudio Server is very common for people running R scripts and R analyses. So to access all the applications, you can just click the Apps menu at the top there. All the other visual apps can, be accessed via loading in a remote desktop. So if you have a piece of software that's more specialized, that may not have a specific button and workflow set up for it on OOD, you can always just start a remote desktop session and load that app directly. In the Files browser, you can actually see a graphical representation of all of the files on your cluster. You can use this to browse, move, create, upload, download, and delete files. If you just need to do something quickly, graphically, this allows you to not necessarily need to open a terminal or SSH into the cluster just to move or upload a couple of files. So in the far right there, we have this button called My Interactive Sessions, and this will show you any of the running sessions you have on OOD. So when you click it, you see sort of a list of different cards that show all the things that you're running, whether it's a RStudio session or a remote desktop. And these sessions are listed here because they do not end when the website is closed. So if you start up RStudio and close the tab and then come back later, when you click the Interactive Sessions button, you'll see that it's still listed there, and there's a button on that card that allows you to click and reconnect to it. So you can close the website, you can reopen on any other computer, connect back to OOD, and pick up right where you left off. The sessions will end eventually. That means either when the requested time runs out, or you click the delete or cancel button in the highlighted card for that session. The status of nodes under the utilities is the utilities menu is one of the most useful options that we have. You can click that and see this massive grid of all of the nodes on your cluster, and it also shows you how in use each of those nodes is. So it will list both the number of CPUs available for each node, as well as the amount of memory that's currently available. So you can see, if you feel that there's something going on, or when your job isn't starting, you can see it might just be that all of the nodes are currently full. You have to wait until some of the priority eases up for your job to be able to start. Under this menu, we also have a few other tools like the get usage readout, the quotas readout, and most importantly, the user portal. And we'll go into more detail on the next few slides with this, but it is a sort of web page that provides a convenient summary of a lot of different important information. So this is the user portal that I just mentioned. I would recommend, bookmarking this page, or at the very least, knowing exactly how to get there from the utilities menu of OOD. And as we work through here, you can see that the first page you see contains a number of different pieces of information that are useful. First is just the name of the cluster, the brief history of why it exists and what its purpose is. We have quick access to the job information of everything that you run today. So if you have submitted jobs on the cluster, you'll see a list of them here, the start time and their current state. We have the information on your storage quotas. We'll go in a little bit more detail on storage quota in just a few slides. But for now, just know that this lists all of the available storage you have to your user and to your group on the cluster. And below that, we have some announcements and upcoming maintenance periods, basically any of the upcoming information and news that you may find relevant to working on this cluster. Now, the menu on the left gives you some more options. For instance, we have the My Groups button, which gives you contact information for everyone in your research group who also uses the cluster alongside you. We have the job overview for more information about jobs that you've recently run. We have cluster usage, which gives you a sort of running total of how much usage your group has used in the cluster. And below that, we have some support links for creating tickets and how to contact my team for support, as well as information about our weekly office hours, links to videos on our YouTube channel like this one, as well as maintenance information and links for common problems, FAQs, and so on. Below this, the documentation link. You can tell it's important because we've linked it, maybe 4 or 5 times now. This is a link to our wiki pages that we try to keep as updated as possible. So anytime we have new software or new problems that people bring to us, we try to keep a documented record of them so that people can reference them in the future. So let's actually begin working in a terminal on the cluster, and we'll learn a little bit about what it is like to interact with a Linux server. So under the clusters menu on the top bar of the OOD interface, you can click the clusters button, and then there's a little link below that that says Open Terminal Session. When you do that, you'll see that this big box opens with a lot of text in it. All of this text that starts with the name of the cluster is called the message of the day, or the MOTD. And this is just another way for us to provide up-to-date information when anyone logs into the cluster directly. So we start with the name. We have some of the permanent information, things that everyone needs to know, and maybe through compliance reasons needs to be displayed each time you log in. These are things like our cybersecurity protocols, the basic information of the cluster, the storage monitoring information, paths to your main directories, as well as any next planned maintenance. You'll see announcements here for that. Below that, we have some of the more pertinent recent announcements, things like upcoming maintenance and reservations on the cluster, upcoming workshops, cluster technical issues that we're aware of and working on. And this section is constantly changing. So it's a good idea to just glance through it as you log in and see if anything's changed since the last time you saw it. So below that, this is the actual prompt, the last line on the screen, which is where you're typing and entering commands. The prompt itself is broken up with some useful information. From the left to right, you have the net ID of the current user. That should, typically be your own net ID as you've logged in. We have the current node you're logged into. As I mentioned, the first node you always log into will be the login node. So here it says login to. It gives you the cluster name, in this case, McCleary, and then the little tilde is the current directory. And in our case, that is a shortcut for the home directory. So in using the terminal, you will be using countless different commands, and the ones that you use most often will be committed to memory, and you'll have no problem bringing them up. But for most of us, people just learning to use the clusters and experts like myself, you'll need to reference things. It's not expected that you remember every single command and the format needed for every one of them. So we're going to be going through just a few of the most common commands, and beyond that, we'll be giving you the tools that you need to look up how to use commands and for any other uses that you may run into. So the first command that we're going to learn is ls. Stands for listing, and its purpose is to list all the files and directories available in your current location. So if you type in ls and hit enter from the home directory, you'll see that it prints out a list of all of the folders and files that are in that directory. So you can see here in the home directory of the test user, we have a desktop folder, a documents folder, downloads, we have a file called hostname.out, we have music, OnDemand, etc. So this is a very commonly used command just to tell what is in the directory I'm currently in. So as I mentioned, the tilde is a shortcut for the home directory, which is its full path is at /home/ your netid. And this is always where you start when you log into the cluster. It stores important links to other key locations, like your project folder, your Scratch folder, which we'll go into a little more detail. For instance, the project directory contains all of the long-term storage for your group, meaning for your lab or your the group of people that work under your PI. So the project directory is shared amongst all members of the group, and most of the work that you do should be completed in the project directory. Your other group members have access to read some of the files here for collaboration, but for the most part, under your specific project folder, that should be the space where you're storing all of the files that you need for the workflows, pipelines, and processes that you're running on the cluster. We also have what's called a Scratch directory, and this is a temporary storage for larger files or files that are works in progress that you may not want to store permanently, but nonetheless need access to while you're trying to run the processes that you're running on the cluster. So the Scratch directory provides a much larger quota of space, meaning that you can store more files there before you run out of space and need to start deleting things, which makes it very useful for temporary storage. If you're, need to load a lot of large data to do an analysis, the Scratch space is a smart place to store it. Under this link, you can find a few more flags, options, and information about the ls command. And in a few slides, I'm going to be showing you how to look up all of those options directly on the cluster as well. So the next command that we're going to go over is also very useful. It's not a built-in Linux command, but it's actually a tool that YCRC developed and built for the clusters, and it's called getQuota. So I mentioned there are a few of these different folders that you have access to. Of course, there's the home folder where you begin, there's the project and Scratch spaces, but what is the difference between these and how do you know where to use and when to use each of them? Well, the primary difference between these different folders is the storage quota available to you. In your home folder, you have just 125 gigabytes of space. That means that you should be storing here maybe scripts, text files, the very final results before you download them out of the cluster. This is not a place that's designed for storing large databases or data for analysis. This is really just the sort of home base for you to have the most frequently accessed files. The home folder is regularly backed up. So anything that you don't want to lose or that is particularly high value and of small size can safely be stored in home. As in contrast to the project folder, which, as I mentioned, is where you're going to be doing most of your work in your group. The quota here is 4 terabytes per group. Older groups that were on the cluster before we raised the limit to 4 terabytes may still have a 1 terabyte limit. If you do run into that, just send us an email. We'll be happy to raise that to 4 terabytes for you. The Scratch folder, as I mentioned, has a much larger limit at 10 terabytes per group. And the downside of that is that it is temporary. We purge data every 60 days, meaning any files that are older than 60 days in the Scratch folder will be deleted. For that purpose, it's temporary. It's only for storing data that you need to access during analysis. And the idea is that any permanent data, permanent results will be stored in your project folder. We have a few extra directories and file systems. The PI storage is available for purchase by PIs and group leaders. So if you ever find that you do need more storage than is available in your project space, we do provide that storage for purchase for PIs, and it allows us to make available to them at a separate directory additional storage. And this can be, it's really limitless how much you want to purchase. That's totally up to you and your PI. For the YCGA, those people running our genome sequencing instruments and storing all of the large data there, they make available to you the data that you submit. So if you are submitting samples to YCGA for sequencing, you'll probably get an email when it finishes that your data is available at one of these YCGA directories, and that's on the McCleary cluster for the life sciences people. And here you have a quota of 4 terabytes. So that's an individual space specifically for working on data that has been delivered back from YCGA. Now, finally, the Yale ITS service also provides storage at Yale. This is a sort of a separate service from ITS that allows you to rent storage that's, I believe, in the AWS cloud. Now, this is only accessible via the transfer node, which is something we'll talk about in just a few slides. But the idea here is that if you are attaching storage for your lab's usage, you can also access it via the clusters. And specifically, this is usually for archival or sort of more long-term genomic data, things that your lab is storing much longer term. And I believe ITS offers up to 30 terabytes of storage through that service. So when you run the get quota command, you'll see a table that contains the information up to date of how much quota is available in each of those directories, as well as what your current usage is. And this is either for your user in the case of your home directory, or for your entire group in the case of all the other directories. So it will tell you that for instance, the Scratch directory has 10 terabytes of storage, and you've used maybe 6 of it. Within each of these lists, you can see the current amount of storage, the files being used by the user and group, as well as whether the current limit has been hit. And if you get near that maximum, you'll see these warning lines down below that tells you, hey, things might stop working in the near future. You should probably reduce your usage so that you don't run into those hard limits. If you do fill these limits, you will typically see that your jobs may fail because they run out of disk space. If your home directory gets full, you might see things like the Open OnDemand dashboard stops loading or doesn't allow you to start new sessions. Anytime you run into this, if you need any help finding files that are large and taking up most of your space, feel free to reach out to YCRC. We help with that kind of thing all the time. So the next useful Linux commands will be cd, and this stands for change directory. It allows you to navigate to different directories. So if you start in your home directory and then you type cd project, you will change directory into the project directory. And the prompt updates so that where before there was the tilde, meaning home, now it shows that you're in the project folder. cd ... will let you navigate backwards to previous directories, and cd- will return you to the most recent directory. Just a few quick shortcuts. The pwd command, which stands for print working directory, just shows you the path of your current location. So if you're in the project directory and you type pwd and hit enter, it will give you the full path from the very top of the file system to your current directory, in this case, home/testuser/project. So this is very useful for pointing commands or scripts or support staff to specific locations for file access. If you know that you're in project folder and you've made some, project 2 folder within that, you can type pwd and get the full list of the exact address of how to find those files. Next, editing text files is one of the most common and useful tasks that we do on the cluster. And the most basic text editor available to you is a program called Nano. So we're going to test Nano out here and create a test.txt file. So go ahead and run the nano test.txt file command, and you'll see that this window opens that has a sort of blank file within it. This is the word processor Nano. It provides some very basic word processing functions for editing text files, and you can navigate things with the arrow keys and type with the keyboard. You'll see down at the very bottom, we have a list of commands. The caret icon means press the control button. So if you are pressing Control O, you will write the file. If you type Control W, that searches for specific text. Control K and Control U will cut or paste text, and so on. So go ahead and enter any text in your test.txt file. In our case, when we created this workshop for the first time, it was around Halloween, so we made some Halloween-themed ASCII art. And once you save your edits, you press Control X for exit. It will ask you to confirm the changes. You press Y to say yes, and then just enter to confirm the file name. In this case, because you opened Nano with the test.txt file name, it's already pre-populated there, and you can just press enter to accept. So we can see that we've created a new file using ls. If we do the same ls as before, we can see now that we have test.txt. So it can be quickly unwieldy to create a lot of files within the same directory. And so we have a command called make directory, mkdir, to create new folders and help yourself organize your files a little bit. So in this case, we're going to create a directory called workshop. And so the command is mkdir space workshop. And then if we run ls again, we can see that the workshop directory now exists. And if we want to cd into it, we can. The next commands that we learn are cp and mv. These stand for copy and move, respectively. So cp copies a file or directory from one location to another, and the copied file will be found both in the original and the new location. Whereas move moves a file from one location to another, meaning it will be found only in the new location and not in the original location. So the syntax for cp and mv is mv space the path to the original file, and then space and the path to the destination. So for instance, I want you to go ahead and see if you can copy the test.txt file that we created from your project directory into your workshop directory that we created. So some tips that you may need as you work on this is use pwd to get the path for each folder so that you can provide it to the cp command. The symbol dot, a period, indicates the current location when used in the cp command. So you can read that as copy here if you write copy dot. And the starting location is the product directory. So you're going to need to cd into your project directory. And the ending location is the workshop directory that we created. So to walk through how I would do this, I would pwd to make sure I'm in the project directory. And then I would cd into workshop. I would copy the full path to the test.txt file to dot, which means the current directory, my workshop directory, and then ls to show that the test.txt file is now present in the workshop directory. So once we've done this, how do we check that the content of the copied file is as we expect? We can obviously open it back up in a word processor like Nano, but it's a little unwieldy to open up a whole program and have to press buttons to exit once again. So there must be commands that allow us to just quickly check the contents of a file. Now, these commands do exist. They're things like cat and less, which we'll learn about now. So the cat command is a command that prints all of the file contents to the terminal. It stands for concatenate, and it's great for showing just short files, quickly copying something, or quickly checking the contents of a file. And all you need to do to use cat is type cat file name. On the other hand, less is a command that's useful for viewing longer files because it allows you to page through a file and scroll line by line or page by page through a much longer file. It also allows you to search with the slash key, and the usage for less is just less file name. Now, we also have the rm command. As you are creating files and using pipelines that create files, you will eventually need to remove files from your file system. So the rm command stands for remove, and it deletes objects like files and directories. The syntax is very simple. You just rm space the file name to delete a file, and rm-r to delete a directory. Otherwise, rm will refuse to delete directories. So just an extra safety feature to ensure that you're deleting the things that you actually think you're deleting. So you will use RM pretty frequently if you're needing to remove unwanted files to stay below your storage quotas. And if you ever accidentally delete files, you can typically recover them if they were snapshotted within the last day or so. The link here gives you a documentation page about snapshots, which are supported for the home and project folders only. So now your next exercise task is to remove the test.txt file from the project directory and use ls to confirm its deletion. Other commands you may need for this exercise, things like cd and pwd. And how I would do this is cd ... to go up one directory from workshop back to the project folder, and then run rm test.txt and show via ls that the folder is now void of the test.txt file. Finally, one of the most useful commands that you can learn and use frequently in Linux is the man or manual command. Now, almost all Linux commands have a user manual that comes with instructions and reference info for how to use that command. So for instance, it's just like using the less viewer. You can page down with space, you can press Q to quit. And in this example, I want to show you the instructions for the rm command. So if you type man rm, you will see this page that says user commands rm, gives you the name of the command you're looking at, a synopsis of the syntax of how to use the command, and then a written description of what the command does. And if you scroll down, you'll also see various options and different ways to use the command that it offers. All right, so let's talk about transferring and downloading files in the cluster. Obviously, a lot of the work that you'll be doing is going to require a lot of data. Your data can either be transferred from lab computers you may already have, it can be downloaded through internet sources, or even transferred between HPC systems on other institutions. So prior to transferring files, it's important that you move to the transfer node. So as we learned before, the first thing you connect to is always the login node. And in this case, we have specific nodes designed for transferring large files. They have a much faster connection to the internet. They have a better configuration for running long download jobs. And so we always recommend that if you are downloading large files or setting up a large file transfer, you first connect to the transfer node. You can do that from the terminal by running ssh transfer, and you'll see that your prompt changes now to list transfer.mccleary as the node that you're connected to. So in more detail, why is it a good idea to step off of the login node before running jobs or running transfers like this? Well, the idea is that the login nodes are really only for directing traffic. When people log in, they maybe move files, make some small changes, nothing that really requires any large amount of computation. And so when a user connects to the login node, they're taking just a small piece of the node, and then when they want to go and run some computation or run a pipeline, they move over to the compute node, which frees up space back on the login node for another user to log in. So the calculations they run are, well designed and take up almost all the resources of the node that they requested, and then they finish. Meanwhile, user 2 log in successfully, and the calculations from user 1 are running on a separate node in the compute area of the cluster and don't affect the login node at all. However, if you do log in and try to run calculations on the login node, you're taking up a lot of space that other users can't use to log in. So when this happens, you might see the sluggish performance on the login node, or even delays in trying to move or copy files or log in. So the login node gets busy when you're trying to run calculations like that, meaning everyone else trying to do things will be slowed down. So typically, we have just for different nodes for different tasks. I've spoken about the transfer node for large file transfers, the compute node where all of the compute jobs run, and the login node is just two nodes that are shared between all of the HPC users for that cluster, which means that they're designed only for logging in and you're doing small things like moving files around, editing files, downloading small scripts, and things like that. We do impose restrictions, meaning there are some systems in place that will detect if you are running computations on the login node and sort of kill your jobs or kill your processes. But it should always be kept in mind that if you're doing anything intensive, anything that may take more than a few seconds or a minute to complete, please do so on one of the purpose-built nodes for that purpose. So let's talk about actually transferring and downloading some files. Assuming that you are already connected to the cluster node, typically if you're just moving things between a cluster, you can use the cp or mv commands that we went over in the brief introduction. There's also a command called rsync, which is like a better, more robust copy command that gives you things like progress updates, can transfer file permissions, and do a lot of more advanced processing and definitions of how you want the files to be copied. Now, if you're transferring from the cluster to the outside location or vice versa, you have a few different options. The Open On-Demand file upload and download, that is when you use the graphical file browser in Open On-Demand, there is a button there that allows you to upload files to the cluster or download files. This is very convenient because you don't have to log into the terminal to do it, but it does have a 15 gigabyte limit, so please keep that in mind. wget is a common command for downloading files from web link directly. So if you type wget and then a link to somewhere on the internet, it will download that file directly into the current directory. That's very useful if you ever have data stored at public storage or a link somewhere on the internet that you just want to download directly to the cluster. You can just copy that link and run wget to download it. We also have a program called rclone, which is useful for moving data from different cloud storage providers. Rclone has a lot of sort of built-in handling for things like Box, Dropbox, Wasabi, AWS, Google Cloud, etc. So with just a little bit of configuration, you can easily copy files to the cluster or from the cluster from each of those services. And that's provided also in our documentation page for rclone. Now, we also have a service called Globus, which is what we use for large databases and any secure transfers. So Globus is a kind of software that sets up different nodes, both in the cluster on your local computer, as well as various other locations like data repositories or other institutions. And so you can log into Globus and set up a transfer and create transfers and collections that you can use to share with people outside of Yale as well and manage the permissions. So finally, we have the option of GitHub. So at the very beginning, we showed you that there's a link to some of the exercise files you'll be working on in the second half of this workshop. The command for there is use git clone and then a link to the repository. We'll be going over that as you start the workshop, but just know that there are a lot of ways to download files and software from Git, and you'll always be using the git clone command to do that. So let's try this. So our location here as the link is github.com/YCRC/intro-2-HPC. And so in the terminal, we're going to go back and log in if you've closed the terminal we were previously working in, cd over to your recently created workshop directory, and then run this command, git clone, and then the link that is above. And when you're finished downloading, exit the transfer node back to the login node. Now, git clone downloads a exact copy of the repository of files listed in the GitHub. So if you go click the link, you can see sort of graphically in your web browser what the files are stored there, what folders exist, what files are within each folder. And when you run the git clone command, you download a full copy of that tree of files to the exact folder structure. So once you've downloaded that, you'll see that in the intro to HPC folder, we have office hour examples. We also have workshop examples. And within that folder, there are further the interactive example and batch example. And these are the two that we'll be working on today in the second half of this workshop. So now that we've done a bit of the introduction of what the clusters are, how to connect to them, some basic usage of how to move things around, connect and create files on the clusters, we'll be going into a little bit more detail on how to actually run jobs and how to actually work through a couple of the workshop examples that we have.
In the second half of our presentation, I'm going to be showing you how to use the tools that Sam shared with you to run actual jobs on our YCRC clusters. This is an overview. I'll be periodically returning to this slide to help keep you oriented on where we are in the presentation. First, I'll show you how to run interactive jobs, which are the easiest way to get going on our cluster and allow you to perform simple tasks that take under a day. Next, I'll show you how to run batch jobs, which allow you to take full advantage of the power of our cluster, including multi-day jobs and jobs that take many cores and run in parallel. Then I'll show you how to evaluate jobs while they're running and afterwards using a tool called Job Stats. And finally, I'll take you through some advanced tips, such as using GPU hardware on our cluster and simple ways to run parallel tasks. And at the very, very end, I'll also give you some tips on how to avoid common pitfalls encountered by users on the cluster and also how to get more help. Quickly, before we get started, I'd like to share with you a few keyboard shortcuts for use with the terminal command line. The command line is something we will return to throughout the rest of this presentation, especially as we get to more advanced tasks, so this can make your life a whole lot easier. First, if you are running a process in an interactive job and it's failing to respond, you can often kill this process by typing Control C. There is also a cousin to this keyboard shortcut called Control Z, but I refer you to additional documentation you can find on the internet if you'd like to use that one. It's a little more advanced with extra functions. More importantly for today are the arrow and tab keys, which have special functions in the command line. The up and down arrow keys allow you to go through your command history, and that's very convenient when you would like to change what you did previously by just a little bit. And you can use the left and right arrow keys to edit those old commands before hitting enter to execute your new command. Finally, we have tab autocompletion on the command line, where pressing tab will finish a command that you've partially typed or arguments for the command that you have partially typed, if possible. If not, if you press tab again once or twice, you will often get a list of possible completions. So this can greatly reduce the amount of typing that you have to do. Now on to interactive jobs. But before I take you through some examples of how to perform interactive jobs in the cluster, you first need to understand a few things about how our cluster operates. And so I'm going to describe Slurm, modules, and partitions now. So what is Slurm? Slurm is scheduling software that is what broadly allows our cluster to equitably share resources amongst the many users who are doing research on it. So the process by which Slurm operates is that you will submit a job request to Slurm. Slurm will then try to find out a way to run it, and while that's happening, the job will be pending. And once it discovers an opening where there is an available node that can run your job, it will start it. And after the job finishes, hopefully successfully, then it will release the resources to allow other users to run their jobs. Unlike your desktop or laptop computer, the HPC clusters, like the ones at Yale, have many, many nodes and many, many cores and CPUs with a diverse set of other hardware that may include graphics processing units or GPUs and other specialized features. So in order to share these resources equitably and fairly, we run a special software called Slurm, which takes care of this for you. And the way that Slurm works is that you will use Slurm to submit a job, and then while Slurm looks for the resources that you need and potentially frees them up from other users, the job will be pending. After that, once Slurm has allocated the resources your job needs, it will start and then hopefully finish at some point later, or it may time out or fail or can be canceled by you, at which point the allocated resources are released so that other users may use them. One of the key features of Slurm is that it divides the computing resources of a cluster into what are called partitions. And this allows users, for example, who want to run something short that may take only a few hours to run their jobs quickly, even if there are other groups of users who have jobs running for a long time, say many days. And it's convenient and necessary for users who have shorter jobs to be able to run them without having to wait. So users with different needs are divided into different partitions. So the partitions that are generally available on our clusters include general purpose partitions, which are available for everyone. And these are the devel partition, which is for interactive jobs that last 6 hours or less. And this we will go into soon in the next few slides. For jobs that could include interactive jobs or batch jobs, which we'll also get into later, the day queue is available, and that's for jobs that run 24 hours or less. And then for longer jobs, we have a week partition available. There are also special use cases partitions, and this includes a partition called GPU, which is available on some of the clusters for hardware that has GPUs. There's a partition called Big Mem, which is for jobs that require extra memory. And then there are MPI partitions, which are specially connected to each other to allow parallel codes to run more rapidly under the circumstances which MPI software uses. Also, there are partitions that belong to specific groups, and these are named PI underscore and then the name of the group. And those are purchased by those groups for use, especially for them. Finally, there is a scavenge partition, and this actually is designed to take advantage of unused resources that can also include the PI partitions. And the way that you use this is that you submit a job to the scavenge partition with the knowledge that it will run if there's any free resources. However, it can be preempted, which means that if the owner of the node or someone with a higher priority would like to use that node, then your job will be terminated perhaps before it's finished. And so you need to take special precautions when using the scavenge node. But the advantage of the scavenge node is that it allows you to run jobs more quickly because there are usually resources that are available. And also sometimes there are many more resources that are available on scavenge. For example, our upper limit of CPU cores per user is 10,000 cores on a given day for scavenge, whereas it's only 1,000 cores per day, for example, on the day partition. For specific information on partitions, and in fact for countless other useful items, it's handy to consult our YCRC user guide, and links for this are posted on the left in this slide and periodically on other slides throughout this presentation. And so here, for example, I'm showing a page on the resources for the day partition of a given cluster where it tells you the limits per user. So for example, here we're seeing that the day partition is limited to 1 day of time. That's in the table under job limits. And the maximum CPUs that any user's group can have running at one time is 2,500, and the maximum CPUs per user is 1,000. Also, we can see the total available hardware for the partition. So at the bottom here, you see that there are 66 nodes with 488 gigabytes of memory on them and 48 CPUs per node. And then below that are other types of CPUs and cores and nodes that are also available in this partition. Software, and particularly scientific software running on Linux, as we have here at the YCRC HPC clusters, can be finicky to set up and run. And this is especially true given the variety of types of hardware that we have available on our clusters. And to facilitate the running of software in this situation, we use a system called the module system, where we have pre-set up thousands of commonly used software packages such that you can run them without having to worry about the type of hardware that you have, and so on. So to use the module system, you would type the following commands into a terminal command line. For example, to load a module for the R software package, you would type module load R, and to give a specific version, you would follow that with a slash and version information. And I'd like to note here that you can often use tab to complete that for you without having to type everything. And if you don't wish to specify a version, you can leave that off, and then a default version will be loaded, which is usually the newest version of that software. You can also see all the available modules that we have by typing module avail, and you can look for specific versions by giving the name of a software. So for here, for example, we have given the commands to list the versions available for MATLAB by module avail MATLAB. You can also see the list of loaded modules by typing module list, and you can unload modules by typing module reset, which is especially convenient when you wish to move on from a current application and go to a new one. Also, if you have software that is not currently installed as a module, we are happy to set it up for you either as a user-owned package, or if there's enough demand, we can make a new module for that application. As I mentioned previously, there are two ways generally to run software on the clusters. We call them interactive jobs or versus batch jobs. For interactive jobs, these are jobs that will take less than a day in general, and you may use these for development of applications as you're testing certain kinds of software or research. Crap. As I mentioned previously, there are two ways to run software on the HPC clusters here at the YCRC. The first way is called an interactive job, and this is commonly used for developing an application where you're still testing your software to make sure it runs the way you want to, or writing new software or debugging it, or also for running software that requires a graphical user interface. And in particular, the open on-demand sessions, which we'll get to shortly, are ways of running on the cluster that are interactive jobs also. And it's important to note that any user is limited to a total of 4 interactive sessions simultaneously, or one of these can be on the develop partition, as I mentioned previously. The second kind of job is a batch job, and these jobs are not interactive, meaning that you can't really change the way they're running once they've started. However, they are much more powerful in the sense that you can run many batch jobs simultaneously. Each batch job can use a lot of resources on its own and can run for many days. And because you can't interact with them, it's convenient to be able to be alerted to when they start or end. And so for that reason, there are options to send emails to you to let you know about that. When you request resources on a cluster, there are a number of options or flags that you can use to control the manner in which the request will run. For the upcoming section where we're discussing interactive requests, we will use the terminal shell command salloc, which is the way that you start an interactive job in a terminal. And the flags that are common to use in this case are as follows. The partition flag, which is abbreviated as -p or fully --partition, is what specifies the partitions that you will use, as discussed in a previous slide. There's the time flag or -t, and that controls how long your request will run for. And this is something that you would set to a generous amount of time, but trying to be respectful of other users, you would not request it to run for too long. And then an important flag is the memory per CPU, which determines how much memory will be requested for your task. And here it's important to note that if you don't request enough memory, your task may die because of an out-of-memory error. However, if you request more memory than you need, then you are also limiting the amount of resources for other users. So it's a balance. Another important flag is the multi-threading option CPUs per task, which is -C. The default for this is 1, but when you have jobs that can be parallelized, as we will discuss, you can increase that number. And related to parallel jobs, there are flags or options that are specifically related to the MPI parallel system. And in that case, you can request the number of compute nodes, which the default is 1, but you can ask for more than 1 node, which increases the number of cores or CPUs that can be available to your task or job. And you can also request a number of tasks for the MPI job, and that's separate from the meaning of the word task I was just using. When requesting When requesting resources on the cluster, there are several options or flags that are useful in controlling the manner in which your job will run. For the following section, where we're going to talk about interactive jobs, the command that you would use on the terminal command line is salloc. The flags that are commonly used for salloc and for other ways of requesting resources are as follows. The partition flag, which is --partition, abbreviated as -p, controls which partition that you would like your job to run on. As discussed previously, these include partitions named devel, day, and so forth. You can also request the amount of time that your job will run for, and that's the maximum, after which your job will be terminated, regardless of whether it finished or not. You can also request the amount of memory per CPU for your job, and this is a maximum again, so that if your job requires more memory than what you allocated in your resource request, then your job will fail. Now, there are other options for parallelizing jobs in the cases where that is helpful. There are two main ways to parallelize, and they are known as multi-threading or MPI. Those are the two kinds. And for multi-threading, the relevant option is CPUs per task or -C. So for applications that have multi-threading capabilities, you can change this number to be greater than 1. For MPI parallel applications, the relevant options are --nodes, which is the number of compute nodes you would like your job to run on. And by increasing this, you increase the possible number of what are called tasks in the MPI application that can be run. And then you also can explicitly set the number of tasks you would like for your job with the --n tasks option. Now that I've introduced you to the basic tools needed to run an interactive job on a cluster, we are going to go through an example of running an interactive job that runs a Python program, a simple Python example. Now, the first thing we're going to do here is we're going to navigate to the workshop directory, and this is where you previously, under the first half of the introduction workshop, where you placed your folder using Git. So that was within your project directory. So I'm going to be using the tab shortcut that I mentioned. So if we type PRO that might be enough to get us project. And yes, when I press tab, we go there. And within project, it was a directory called workshop, and pressing tab gets me there. And now within there, there is a directory called intro to HPC. And at that point, we need to know more. If I press tab, there are more directories than that. But if I press tab, I see what those choices are. And so we want the directory called workshop. And if I hit return, now we have workshop examples. I can type ls. And our first example is going to be the interactive example. So I will go into that directory again using tab. And now if I type ls, we'll see there's exactly one file in here, which is the one we want. Okay, so now we would like to allocate some resources in order to try this example. So we will type salloc, and then we'll give it a time specification, which is 1 hour in this case. And now we are on a compute cluster, as you can see from the prompt here, where it says R209, U08, N03 on McCleary. And now, in order to run this, we actually need to get Python. So we can load the module for that, and that would be module load Python. And here again, we can press tab. So if I type PYT and then press tab, boom, we get Python. And then maybe we'd like a particular version. So I can press tab here again. And there are all the versions that are available. And I would say that for us, let's try 3.12. Press tab. There we go. Now, if you type module list, you will see the list of Python and its required modules. Unlike your desktop or laptop computer, the HPC clusters, like the ones at Yale, have many, many nodes and many, many cores and CPUs with a diverse set of other hardware that may include graphics processing units or GPUs and other specialized features. So in order to share these resources equitably and fairly, we run a special software called Slurm, which takes care of this for you. And the way that Slurm works is that you will use Slurm to submit a job, and then while Slurm looks for the resources that you need and potentially frees them up from other users, the job will be pending. After that, once Slurm has allocated the resources your job needs, it will start and then hopefully finish at some point later, or it may time out or fail or can be canceled by you, at which point the allocated resources are released so that other users may use them. One of the key features of Slurm is that it divides the computing resources of a cluster into what are called partitions. And this allows users, for example, who want to run something short that may take only a few hours to run their jobs quickly, even if there are other groups of users who have jobs running for a long time, say many days. And it's convenient and necessary for users who have shorter jobs to be able to run them without having to wait. So users with different needs are divided into different partitions. So the partitions that are generally available on our clusters include general purpose partitions, which are available for everyone. And these are the devel partition, which is for interactive jobs that last 6 hours or less. And this we will go into soon in the next few slides. For jobs that could include interactive jobs or batch jobs, which we'll also get into later, the day queue is available, and that's for jobs that run 24 hours or less. And then for longer jobs, we have a week partition available. There are also special use cases partitions, and this includes a partition called GPU, which is available on some of the clusters for hardware that has GPUs. There's a partition called Big Mem, which is for jobs that require extra memory. And then there are MPI partitions, which are specially connected to each other to allow parallel codes to run more rapidly under the circumstances which MPI software uses. Also, there are partitions that belong to specific groups, and these are named PI underscore and then the name of the group. And those are purchased by those groups for use, especially for them. Finally, there is a scavenge partition, and this actually is designed to take advantage of unused resources that can also include the PI partitions. And the way that you use this is that you submit a job to the scavenge partition with the knowledge that it will run if there's any free resources. However, it can be preempted, which means that if the owner of the node or someone with a higher priority would like to use that node, then your job will be terminated perhaps before it's finished. And so you need to take special precautions when using the scavenge node. But the advantage of the scavenge node is that it allows you to run jobs more quickly because there are usually resources that are available. And also sometimes there are many more resources that are available on scavenge. For example, our upper limit of CPU cores per user is 10,000 cores on a given day for scavenge, whereas it's only 1,000 cores per day, for example, on the day partition. For specific information on partitions, and in fact for countless other useful items, it's handy to consult our YCRC user guide, and links for this are posted on the left in this slide and periodically on other slides throughout this presentation. And so here, for example, I'm showing a page on the resources for the day partition of a given cluster where it tells you the limits per user. So for example, here we're seeing that the day partition is limited to 1 day of time. That's in the table under job limits. And the maximum CPUs that any user's group can have running at one time is 2,500, and the maximum CPUs per user is 1,000. Also, we can see the total available hardware for the partition. So at the bottom here, you see that there are 66 nodes with 488 gigabytes of memory on them and 48 CPUs per node. And then below that are other types of CPUs and cores and nodes that are also available in this partition. Software, and particularly scientific software running on Linux, as we have here at the YCRC HPC clusters, can be finicky to set up and run. And this is especially true given the variety of types of hardware that we have available on our clusters. And to facilitate the running of software in this situation, we use a system called the module system, where we have pre-set up thousands of commonly used software packages such that you can run them without having to worry about the type of hardware that you have, and so on. So to use the module system, you would type the following commands into a terminal command line. For example, to load a module for the R software package, you would type module load R, and to give a specific version, you would follow that with a slash and version information. And I'd like to note here that you can often use tab to complete that for you without having to type everything. And if you don't wish to specify a version, you can leave that off, and then a default version will be loaded, which is usually the newest version of that software. You can also see all the available modules that we have by typing module avail, and you can look for specific versions by giving the name of a software. So for here, for example, we have given the commands to list the versions available for MATLAB by module avail MATLAB. You can also see the list of loaded modules by typing module list, and you can unload modules by typing module reset, which is especially convenient when you wish to move on from a current application and go to a new one. Also, if you have software that is not currently installed as a module, we are happy to set it up for you either as a user-owned package, or if there's enough demand, we can make a new module for that application. As I mentioned previously, there are two ways generally to run software on the clusters. We call them interactive jobs or versus batch jobs. For interactive jobs, these are jobs that will take less than a day in general, and you may use these for development of applications as you're testing certain kinds of software or research. Crap. As I mentioned previously, there are two ways to run software on the HPC clusters here at the YCRC. The first way is called an interactive job, and this is commonly used for developing an application where you're still testing your software to make sure it runs the way you want to, or writing new software or debugging it, or also for running software that requires a graphical user interface. And in particular, the open on-demand sessions, which we'll get to shortly, are ways of running on the cluster that are interactive jobs also. And it's important to note that any user is limited to a total of 4 interactive sessions simultaneously, or one of these can be on the develop partition, as I mentioned previously. The second kind of job is a batch job, and these jobs are not interactive, meaning that you can't really change the way they're running once they've started. However, they are much more powerful in the sense that you can run many batch jobs simultaneously. Each batch job can use a lot of resources on its own and can run for many days. And because you can't interact with them, it's convenient to be able to be alerted to when they start or end. And so for that reason, there are options to send emails to you to let you know about that. When you request resources on a cluster, there are a number of options or flags that you can use to control the manner in which the request will run. For the upcoming section where we're discussing interactive requests, we will use the terminal shell command salloc, which is the way that you start an interactive job in a terminal. And the flags that are common to use in this case are as follows. The partition flag, which is abbreviated as -p or fully --partition, is what specifies the partitions that you will use, as discussed in a previous slide. There's the time flag or -t, and that controls how long your request will run for. And this is something that you would set to a generous amount of time, but trying to be respectful of other users, you would not request it to run for too long. And then an important flag is the memory per CPU, which determines how much memory will be requested for your task. And here it's important to note that if you don't request enough memory, your task may die because of an out of memory error. However, if you request more memory than you need, then you are also limiting the amount of resources for other users. So it's a balance. Another important flag is the multi-threading option CPUs per task, which is -C. The default for this is 1, but when you have jobs that can be parallelized, as we will discuss, you can increase that number. And related to parallel jobs, there are flags or options that are specifically related to the MPI parallel system. And in that case, you can request the number of compute nodes, which the default is 1, but you can ask for more than 1 node, which increases the number of cores or CPUs that can be available to your task or job. And you can also request a number of tasks for the MPI job, and that's separate from the meaning of the word task I was just using. When requesting When requesting resources on the cluster, there are several options or flags that are useful in controlling the manner in which your job will run. For the following section, where we're going to talk about interactive jobs, the command that you would use on the terminal command line is salloc. The flags that are commonly used for salloc and for other ways of requesting resources are as follows. The partition flag, which is --partition, abbreviated as -p, controls which partition that you would like your job to run on. As discussed previously, these include partitions named devel, day, and so forth. You can also request the amount of time that your job will run for, and that's the maximum after which your job will be terminated, regardless of whether it finished or not. You can also request the amount of memory per CPU for your job. And this is a maximum again, so that if your job requires more memory than what you allocated in your resource request, then your job will fail. Now, there are other options for parallelizing jobs in the cases where that is helpful. There are two main ways to parallelize, and they are known as multi-threading or MPI. Those are the two kinds. And for multi-threading, the relevant option is CPUs per task or -C. So for applications that have multi-threading capabilities, you can change this number to be greater than 1. For MPI parallel applications, the relevant options are --nodes, which is the number of compute nodes you would like your job to run on. And by increasing this, you increase the possible number of what are called tasks in the MPI application that can be run. And then you also can explicitly set the number of tasks you would like for your job with the --n tasks option. Now that I've introduced you to the basic tools needed to run an interactive job on a cluster, we are going to go through an example of running an interactive job that runs a Python program, a simple Python example. Now, the first thing we're going to do here is we're going to navigate to the workshop directory, and this is where you previously, under the first half of the introduction workshop, where you placed your folder using Git. So that was within your project directory. So I'm going to be using the tab shortcut that I mentioned. So if we type PRO, that might be enough to get us project. And yes, when I press tab, we go there. And within project, it was a directory called workshop, and pressing tab gets me there. And now within there, there is a directory called intro to HPC. And at that point, we need to know more. If I press tab, there are more directories than that. But if I press tab, I see what those choices are. And so we want the directory called workshop. And if I hit return, now we have workshop examples. I can type ls. And our first example is going to be the interactive example. So I will go into that directory again using tab. And now if I type ls, we'll see there is exactly one file in here, which is the one we want. Okay, so now we would like to allocate some resources in order to try this example. So we will type salloc, and then we'll give it a time specification, which is 1 hour in this case. And now we are on a compute cluster, as you can see from the prompt here, where it says R209, U08, N03 on McCleary. And now, in order to run this, we actually need to get Python. So we can load the module for that, and that would be module load Python. And here again, we can press tab. So if I type PYT and then press tab, boom, we get Python. And then maybe we'd like a particular version. So I can press tab here again. And there are all the versions that are available. And I would say that for us, let's try 3.12. Press tab. There we go. Now, if you type module list, you will see the list of Python and its required modules. Now we are ready to run our interactive Python example. So first, let's have a look at it. I'll type ls to remind ourselves of the name. So now we'll use nano. I'll type I and then tab to get the name. And here we have Python code. If you're familiar with it, you'll see that at the top here, we have defined a function called message decode tutorial. It inputs a string and a count, which is, it's going to take every cth letter and decode the message by printing that. And so you see that the message to decode is this string here. And then we're going to call the function looking for every 10th letter, and then we're going to print the cipher. Okay, looks great. Let's try it. Okay, so we'll type Python, and then the name of the Python script, I tab, hit return, and oopsie, we have an error here. Luckily, Python is very descriptive in terms of printing error messages, and so it tells us we're expecting a colon at the end of this if statement, which is certainly true for Python. So let's go back and have a look and fix that error. So nano, actually, let's use the up arrow here. So, okay, so we got back to this command, hit return, and let's navigate down to the problem statement, and we're going to type a colon. Let's exit and save. Yes. And now let's try that again. So up arrow to get back to the Python command. And now let's hit return. Look at that. We have a legible message. Mission complete. Now, one last thing, very important. We're done with this example, and now we want to release the resources. So we're going to log out of this compute node, which we can do by typing exit. We can also type Control D if you want the shortcut, and we're done. Returning to our overview, we've now completed the Python example, and now I'd like to show you how to run interactively jobs using our open on-demand graphical interface. And I'll show you how to launch Jupyter for interactive Python programming that way. And just to note, we're not going to actually run anything on Jupyter. This is just to show you how to launch it. So first, let's go to the Open On Demand main page. And you can see here the address for that, ood-mccleary.ycrc.yale.edu/pun/sys/dashboard, or you can get to that from our documentation. And so what you're going to see here is uh, a list of apps. That's what we're going to be working with right now. And then importantly, there's also a menu up here with a much longer list of apps, which you can access by clicking on all apps. There's also a handy file interface. Then there's a way to access your active jobs. There's another menu for interactive apps. And then you have utilities, some of which we'll get to today, and then other things. And this includes launching the interactive shell, which we have done. So, okay. So if we would like to launch a Jupyter session, then we will click on this button here. And here we have the panel where we're going to request a session. And so this actually gives options for the the Slurm menu, the Slurm options that we've seen before. And so if you look down at the bottom here, there's a place where you can enter the number of CPUs per node that you'd like to use, and also the number of hours for your session and the memory per CPU, and the partition, which is also important. And so here we'll use the devel partition. We're going to be running less than 6 hours. We're actually just we'll need much less than 1 hour, and we don't need many resources. We're, as I said, not going to actually do anything. And so up here, we just have environments, and I'll be showing you in a moment how we can actually add to this list of environments using Conda. But for the moment, we'll just go with our default environment, and let's launch this and see what it looks like. Okay, and so now we have to wait while Slurm looks for a slot for your job. And this takes about 10 seconds usually. All right, and now it's instantly given us something that we can connect to. So we'll click on Connect to Jupyter. Okay, so now if you're familiar with Jupyter, we have a file menu that it starts off with, and you are able to start sessions and so on. And that's that. So, and now to exit this, which will also conclude your Slurm session, you can log out or shut down, or even just close the window. So we'll shut down. Okay, and then to really end this session, we will delete it. Now, I'd like to show you how to create custom environments using Conda with that same interactive Jupyter session. So Conda is a very versatile way to expand the abilities, the capabilities of Python, and it's really one of the main standards for scientific programming. So we encourage users to create Conda environments and install packages using the following method. So firstly, I'd like to note that it's very important that you run these Conda commands on a compute node, because it's surprisingly resource intensive for Conda to do all this work. And so the procedure that you will do is you'll activate a compute node with salloc. And then we have a module for Conda. So you do module load mini Conda, and then you will use a command like the following to create an environment. Here's the name, env name, and then you will list Conda packages that you would like to include in your environment. And thereafter, once you have created the environment, you can activate the environment. And then is when you can start using it in your terminal, where this will be happening to begin with. And you can also install additional packages once you have activated the environment. And you can even use pip to install packages. And that can be handy when Conda doesn't give you exactly what you need. And then in subsequent sessions, once you have set up your Conda environment, you simply need to repeat the following commands. Module load miniconda gives you the module, and then you can activate your environment, and then you can start using it to run Python code, for example. So now I'd like to show you how you can install a Python environment like this, firstly from the terminal, and then I'll show you how you can put it onto your Jupyter environment. So now let's see that in action. So we're going to create a Conda environment. And so firstly, and very importantly, we're going to get onto a compute node interactively so that we can take care of the resources Conda needs without interfering with other users. Now we need to load the Conda module. So we'll do module load mini Conda. Okay. We see that we have it. And now we'd like to create a Conda environment. So let's try that. So Conda create, and we'll give it a name, test env, and then we'd like Python equals 3.11, let's say, and then we'll have pandas, numpy, scipy, and let's see what happens. So now we'll proceed by typing Y. All right, and now it's finished. This takes a couple of minutes for us, but we have cut that out for the video. So now we are ready to try this environment, and so we can actually load this version of Conda, which should be almost identical to what we had before in the previous example. So we'll do Conda activate test env. Now we have a Conda Python, which we can run on our interactive example. And it still works. Great. Now, the next thing we'd like to do is to make this accessible to the Jupyter interactive open on-demand app. And so if we return to the website, now you can see that just below the menu here, where it's the environment setup, there are instructions that tell you exactly how to do this. And so we have created a Conda environment. And so in order to make that Conda environment work with Jupyter, you actually have to do two things. You have to add Jupyter and Jupyter Lab to your environment, which is straightforward. We'll just do that in a moment. And then you have to run a YCRC conda env shell command in order to put that into the menu here. So let's do those things. Okay, so here we are in the interactive example directory where we were before. And first, we're going to, very importantly, get onto a compute node using salloc because of the resources conda takes. Okay, now we'd like to load the miniconda module. And then we're going to activate the environment we just made. So conda activate test env. Okay, now we'd like to add Jupyter and Jupyter Lab to that environment. So here we go. So conda install Jupyter and Jupyter Lab. Yes, please. Okay, so we have updated the Conda environment. And lastly, we would like to put that into the Jupyter menu. So we'll do YCRC conda env.sh update. There. Now, when we return to the Open On-Demand Jupyter app, first let's refresh it just to be sure it works. Okay, and now we have two environments because I had made one before, but the new one is test env. And so now when you run Jupyter, you will have access to those additional Python functions. Now that we've explored interactive jobs on our YCRC clusters, it's time to look at batch jobs. And I'll take you through a simple example of how to make one of these and run it. So there are three commands that you will return to when you are working with batch jobs and Slurm. So sbatch is the command you'll use to submit a batch job, which you give your script name, and it will return to you a job ID, which is how you will identify it. Second, there's sq, which is the Slurm command that lists running jobs, and if you give it the --me option, that will tell you all of your running jobs. And finally, you have scancel, and then you give it the job ID, which you can obtain either from what you got when you ran sbatch or by the sq command. And that allows you to cancel a job that you have queued that you no longer wish to run, or to kill a running job. Now, the same flags that we introduced you to before for interactive sessions are also relevant here, including the partition, time, memory, multi-threading, and other parallel options. However, in addition, the options that we will like to use for batch jobs include specifying the job name with --job name, or --output to specify the name of an output file, which is basically the output of your command. And finally, you can tell Slurm to send you emails when your job has started and when it's finished. Those are very convenient. So the main thing we need to do now is to understand how to set up a batch script, which is just a text file that specifies how to run your job. This tells Slurm the necessary information. And the key thing about this is that you put a series of lines at the top of your script. The first one is what tells Slurm what kind of script you're running. And for all of our examples, we will use bash, which is just a standard shell command. And then you have lines that specify Slurm options. And so they start with the pound sign followed by capital SBATCH, and then all the options that you wish to specify. So here, for example, we have the name of the job, specifying the develop partition, a 12-hour time limit, and to send emails for every step of your job. And after this in your script, you just give the commands similar to the ones that we did interactively in our terminal examples. So now we're going to take you through an exercise. So feel free to pause here and do this example by yourself. And then when you're ready, I will take you through it as we would do it here at the YCRC. So starting from where we were before in the interactive example, let's just go up one directory. That is done by giving two periods to the cd command. So now we're in the upper level directory called workshop examples, where you can type ls and see that we have other example folders. And here we will go to the batch example. And if we type ls here, you'll see a set of files. Now, what we've set up for you here is a file called xslurm.sh. That is the file that we wish to run. but it has some things we still need to do. And then for convenience, we also have the solution file here. We're not going to look at that. That would be cheating. So let's have a look at xslurm.sh. All right. So what we need to do here is to edit the directives that tell Slurm how to operate. So we'd like to run this on the devel partition. So we'll specify that. We'd like a measly 1 gigabyte of RAM. So remember here that to specify the units, because if you don't, it happens to default to megabytes, and if you forget that, you may wind up with not as much RAM as you would like. We need to specify the time that we'd like to run this for. So we'll say 20 minutes. That's plenty for this job. And then we would like to tell it to send email in all steps of the job. Now for the business end of this script, we would like to first we'd like to reset any modules that have been loaded. So we will say module reset. Now we would like to load R. So here we can just say module load R, and we could give the flavor of our, like the version number if we wanted to, but the default should be fine here. And now we need to run our R script, and let's see. So that one happens to be called mc.r, which I should have shown to you, but we'll confirm that in a moment. And that should be it. So now we will save and exit. Yes, xslurm.sh. And so there, by the way, is the R script that we wish to run. So now let's have a look at that to see what we're actually running. And so this is a Monte Carlo simulation to estimate the value of pi. So the way it does that is it goes through a loop and it places random points and decides whether they are within a circle or not, within a square region, and then it counts points inside and outside the circle and calculates pi that way. So let's see how it works. Now, firstly, we might ask, do we even really need to use a batch command for this? So we can actually try to run this by an interactive command. So why don't we just try that? So why don't we just try source xslurm.sh? Okay, so now we can see it reset the modules and it's just kind of hanging out. We're waiting for something to happen and it's not doing anything. So I'm starting to feel a little impatient here. So I'm going to show you how to stop this with Control C. Okay, now we interrupted this job rudely and we see a bunch of error messages, which we won't worry about. We just have to know that we stopped the job and it made it a little unhappy. But so what was actually happening? So if we go back and look at our script, what was the next step? So after module reset, it looks like we're loading R. Now, it turns out that R is a kind of a slow module to load. In fact, it takes about 40 seconds on our system right now. And so, I'm not really happy with this because I want to find out if the script works. I don't want to spend all my time waiting to load this module. So let's just have a look at our documentation and see if there's anything about fast module loading. And here I'm just giving you an example of how you might in your workflow encounter questions like this. And the search box in our documentation is very handy here for that. So let's just type fast module and look at that. There's something on loading modules quickly. And in fact, it turns out that we have just recently implemented a way to load modules faster. And it gives us some instructions here. We want to load a special module called MLQ. And then we should just be able to load modules more quickly. So let's go back here and try that. So let's load this MLQ module. Okay, and now let's try loading R this way. Okay, and that loaded very quickly. And so now we can actually just use R to run this mc.r scripts interactively. And now we see it start to run, and oh, it got to 1%, 2%. So this is kind of a slow job. So it really does seem appropriate to submit this as a batch script. So I'm going to type Control C and terminate this. And now, since we're going to run a batch script, we don't need to be in an interactive compute node anymore. I'm going to exit the compute node because we're actually going to claim a compute node with our sbatch command. So, whoops, we're now in the wrong directory. Let's go back to the batch example. See where we are? Okay, so we have edited that batch script, so it should run. So let's try that. Sbatch x slurm.sh. Okay, it has been submitted. We have a job number. So now let's have a look in the queue with this command. And voila, you can see that it's running. That's good. So let's have a look at what's now in a directory, and we see that there is an output file. Okay, so let's have a look at it. We can use cat. And oh no, look at that. It's resetting the module and now it's still loading R. So why don't we cancel this and just update our Slurm script to use the fast module loader. So nano x slurm.sh. So now we will just change this and we'll say module load MLQ. And then we will replace module load with fast module loading command. We'll save this. And now let's just make sure that that the queue is cleared out as we hope it should be. There's nothing there. And let's try the up arrow here to get back to the batch submission command, sbatch. So now we've submitted it again. And so if we type sq-me, it's now running again. And if we look now in our directory, there's a second Slurm output job. Since we terminated the first one, we now have to look at the second one. And let's see how that one looks. All right, now it's running and it loaded that R module very quickly, which makes us happy. So now we just have to wait for it to finish, and you can see that we can follow the output. We can actually use this command tail -- follow to follow it in real time. So now we're looking at getting to 15, 16, and so on. So soon it will be done. Now, while that job is running, I'd like to introduce you to our job monitoring method, which is called job stats, which is very convenient for assessing how your jobs are running. So to do this, we're going to go back to Open OnDemand, return to the main Open OnDemand page. We will go to the Utilities menu, and now we're going to select User Portal. And so we can see here a list of jobs that have run in the past and one that is currently running down here. This would be our job. So now to have a look at it. First, let's just look at what else we have here. We have a convenient listing of our file usage. And so, for example, we see that on this row here, um, our home directory has only 5 gigabytes used of our 125 gigabyte quota. We see that we've used a fair number of files, which is actually due to Conda, which is another story, out of a total of 500,000 files that are allowed. And we also have news of various sorts at the bottom. So the main purpose for now, though, is to have a look at this job. So I will click on the job ID, which is the same as what you saw from the terminal. And so we have various information about this. And at the top is the text listing where you see CPU usage and memory usage. And then we have it in graphical form down here. And what's very heartening to see is that the CPU usage has maxed out at 100%, so we're not wasting CPU cycles, which is great. And we aren't using very much memory at all, but we only requested a gigabyte, which is a small fraction anyway. So that should be fine. Now, if we return to the terminal, I'd like to show you the other way that you can monitor your job more directly. And I'll type Control C to stop this monitoring we're doing with the tail command I showed you previously. But we can log on to the compute node where your job is running. So I'd like to show you that. So let's remind ourselves of where that would be. So if you do sque --me, then you can find the job ID, and you can also find other information like how long it's been running and so on, as well as the node that it's on. And so if we type SSH and then the name of that node, now we are on the compute node where your job is running, and it can be convenient to monitor things about it from there. And the command we'd like to use here is called htop. And if we type htop and then our username, which here is test user, now we get some handy statistics about what's happening with our job. And most relevant for us here is we see that there is a process, which happens to be R, that's taking almost 100% of the processor of a single processor. And that's as it should be. It's taking very little memory, and that's also as it should be. Returning to the user portal, we can go back to the home page here. And now we see that our job has completed. So returning to the terminal, you can see that it has printed out a sort of accurate approximation of pi. That's kind of cool. I'll type Control C to end the tail command we were running. And now we are complete with this example. I'd like to show you one more thing, which is how to look at job statistics from the terminal. And so we have at the YCRC a command equivalent to what you just saw on our Open OnDemand page. And so if you have the job ID, which is listed, for example, in the Slurm output file name, as well as the other ways I've shown you, you can type the following. You can type the following: job stats, and then give your job ID. And now you see that you have a text output that you can look at after your job is finished. It's very convenient. And you see that the overall CPU utilization was near 100%, which is good. And then it gives you all these other nice details about your job, which allows you to quickly overview it, even while it's running, but also after. And this can give you a sense of how well you did. Now, there's one other topic I'd like to touch on here, which has to do with parallelization. So you might ask, could this job run faster if it were parallelized? So it's easy to add that as an option in our batch script. So if we look at it again with nano xslurm.sh, you can see that we requested one processor, Well, in fact, it's not listed here as an option, but say we would like to request more than one processor. We could do it this way. We could ask for another core with the -C, and then we'll give it 2 cores as an option. Now, not every task parallelizes well. R contains parallel features, but it actually sometimes takes additional coding work to access them. Python is similar, that sometimes it will parallelize what you're running, perhaps in NumPy, and sometimes it does not. So let's say we would like to ask whether this job works more effectively when parallelized. So I will save this. And let's try running it again. And now we will use job stats to ask whether the additional core is being used. And this is very important when you are trying to do parallelization with your computation. And we highly recommend that if you are trying to do something that could take advantage of many cores, to start small. Start with, say, 2 cores, and then run the evaluation that I'm about to show you in order to ensure that it's doing what you want. And this will save you a lot of time. So let's use the arrow keys to submit this one again. Actually, there it is. Let's see if it's running. And it's running. So now let's return to the user portal and let's look for our new job. In fact, we can refresh the page, and then it looks like we need to go to the next screen here. And there's our running job. So let's have a look at the CPU usage there. And let's see how we did. And now look at the efficiency. CPU usage percentage is at 50%, which is only one of our 2 processors. So we can see that the parallelization didn't really work here. And to request 2 compute nodes doesn't give us anything. And in fact, it consumes unnecessary resources. So in summary, I've showed you how to monitor your jobs in job stats, which is especially useful for batch jobs, but could also be useful for interactive jobs. And I've shown you how you can monitor jobs while they're running. And you can actually investigate not only CPU information, but GPU information that way. And also after your job is completed. And that can help you give information not only about how successful it was, but how long it took to finish, how much memory it used, and how efficiently did it use those CPUs and GPUs in total. And this is wonderful for helping you make your jobs run faster and to optimize your resource utilization, which basically also helps you share the resource, be considerate in the way you share your resources with other users who are also trying to do the same thing. It's very useful for troubleshooting your jobs as well and seeing if something has gone wrong. And importantly, we encourage you to use this tool to request less resources when you don't need them, for example, memory. And this will also help you reduce wait times for starting your jobs, because the less resources you request, the more likely it is you will find an available resource. So that concludes my discussion of job stats. And so finally, I'd like to take you through some tips for more advanced resources on our clusters, namely GPUs and methods of parallelization. And this is just really brief. So to use a GPU for the YCRC clusters, you will have to add additional Slurm options. And so these are the ones that you need to know. And also you will need to request the appropriate partition. And so the common resources that are available to everyone on the YCRC clusters are called GPU_devel for interactive jobs that lasts less than, say, 6 hours. And then GPU, which is where you can submit batch jobs. And actually on one of our clusters, you can also submit interactive jobs on GPU. The flags that you would like to use for this are the dash dash GPUs flag, which is how many GPUs you are requesting. It also allows you to specify the type of GPU, as we've shown here in this example, where an A100 is requested. You can also specify the number of nodes, and this is handy if you are requesting multiple GPUs, although note that many of our nodes have multiple GPUs on them. You can also specify the number of CPUs per GPU in addition to the ordinary specification where you would just request a certain number of CPUs. And you can also constrain the GPU types, which is a more flexible way of specifying what sort of GPU you want, as opposed to the dash dash GPUs option. And as noted before, job stats can be used to monitor GPU utilization, and so we heavily encourage you to do that. The final topic here that I will just mention briefly is parallelization through the use of Slurm job arrays. And I encourage you to go to our documentation for more information on this. But just briefly to note that sometimes parallelization is not very hard. Often it may involve extra coding, but in the case of what we call embarrassingly parallel jobs, it may only be that you need to run the same script 1,000 times with just a different number. Like you can tell the script to run the first job, the second job, and so on. And if they're independent of each other, that can be done very simply through this method. And it's most convenient on our cluster to use a tool called DSQ, which is actually a module. So you will module load DSQ to get started with this. And DSQ allows you to submit a job with one job ID, but it'll have many sub jobs that are specified by indices. And so it also allows you to gather statistics on the jobs that are running and say some of them have failed for some reason and some of them may not be complete. You can gather all this information on the fly and after they're done, which may help you to finish jobs that only partially completed, for example. So again, I encourage you to go to our documentation to investigate this further. So that concludes all the topics I've listed. I'll just make a few more notes. There are more exercises available. If you'd like to go through our more advanced examples, then I encourage you to go to the directory that's listed here in the Intro to HPC directory under Office Hour Examples. And there you can explore running R scripts in an interactive open on-demand session, R Studio, as well as in the terminal. You can also see what it's like to run MATLAB with a display and without. And there are more examples for Conda environments and open on-demand Jupyter. So finally, your journey is unlikely to be totally smooth as you are learning this environment. Here are some of the common issues that new users, especially new users, but even us from time to time encounter. So firstly, please do not do conda commands like making environments or compiling software on login nodes. That consumes resources which quickly eat into other users' ability to do simple tasks on our cluster. These need to be done on compute nodes. Secondly, applications like RStudio and OnDemand may stop responding, but RStudio in particular is a little bit notorious for this. And if you find that you are submitting an open on-demand job for RStudio and it's not responding, then you may have to just stop your session and run the shell command YCRC clean RStudio in the terminal. And often that fixes issues where you just can't run the RStudio session. It just stops or stalls. So another issue is if you're unable to create Conda environments or run on-demand apps, this is often because you have run out of file storage, and you can use our command get quota, which I encourage you to search in our documentation for more info on that. And the two types of issues you may run into is that you have simply consumed all your storage space on your home directory, But also Conda by itself can actually fill up your directory just with a huge number of files and exceed your quota, not because the storage is full, but because we have a limit on how many files can be stored. And if that happens, please contact us and we'll help you sort that out. You can also run into issues if you try to run too many interactive sessions, because our limit is on YCRC clusters is 4 interactive sessions total per user and 1 interactive session on the devel partition. If you have other issues that you cannot resolve, please reach out to us at hpc@yale.edu and we'll be more than happy to assist you. Finally, I'd like to direct you to our website for additional resources. So in addition to the user guide that I've pointed you to and the YCRC home website, we have office hours every Wednesday from 11 a.m. to noon, where 2 of our staff will be happy to help you work on your short questions and get you going on various tasks you may need. We also have a training website, and we run numerous courses throughout the year, and those are listed on the website. And you can also consult videos from prior trainings that we have done, like this one. We are looking forward to working with you to help you run your computations as smoothly as possible. Please reach out to us if you require any assistance. Thank you for listening and have a great day.